I am starting my timer. It's going to be a 20-minute video. When the alarm goes off, I'm going to stop wherever it stops, guys. So what's important about this document, this is what it shows there. They used a Toray product, T8, T800S, right? Oh, sorry, that was not the timer. That was quick, wasn't it? And then it's a glue system they should use also. All right. Now, but what's important in this thing is the way they did the layout of this. And what they did was they used OceanGate had as received rolls slit into 1/2 inch width reels, toes. So 1/2 inch. Now all the specifications, the testing on this for the standard for this company, they don't test it at this 1/2 inch. From what I can find, they do not do that. So here, look at the cured thickness is, wow, it's way down there at 10,000ths of an inch, 0.0075 inch. It really comes out, the fibers really thin. So to someone asked me, do they also have to scale down the plies? I'm sorry, scale down the layers. So your answer is yes. On the 1/3 scale, you would have to scale down that, and also to the 1/3 to do the 1/3 testing. And they didn't do that. But this is a 1/2 inch, which is, they would have to test this material on the 1/2 inch to see how it behaves. But this is the report from the materials laboratory, and they're going to tell us the direction right here, the winding right here, how they applied it, direction and bias. That's the cat in the background. That's Max. Were reversed on the following. Were reversed on the following cylindrical plies. There were no 45-degree torsion plies. All right, this is crazy. And so he said he didn't do that, but in one of his models it was. I believe the first one the guy did do the plies, because Rush believed there's no torsional forces in the ocean. So this explains why also this thing took place, torsion took place, rotational torque took place during the failure. It says that the plies were 133 plies had been applied to produce a nominal thickness of almost 1 inch there. 1 inch thick layer with the intermediate debulking steps included during the build. All right, debulking steps, his word debulking, I'm going to not try to define his word debulking. I'm not going to define it clearly. It could mean multiple things, from putting the vacuum bag, tightening it up, etc. But more importantly is the way he laid this out. He said the toes for the cylinder were wound continuously from end to end. So it sounds like this, as formed in a helical path, slightly biased off the cylindrical direction. Meaning if you just go, if we look at the top of the reel, and I want to put this band on it, I just can't do this and move over to the next one. Think of it like a screw. It's got to be a thread. I've got to now go like that. I've got to be able to, as it comes back. I'm not going to go backwards, but it's going to move over just a little bit to keep going. See the screw effect to get the layers, and in this distance here, the overlap matters. I don't know what the overlap is. They would know that. All right, so they did that direction. The toes in the silicone pier were continuously wound from end to end. As such, formed a helical path, slightly biased off the cylindrical direction. It had to be to move to the next, move over one, at least a position. Well, I don't know the overlap. The winding direction and bias were reversed on the following cylindrical plies. So then it turns out they then, instead of going like this, they then went like that. These things, what's the point of that? You're creating you think you're creating a counter to it, or more rigid. The testing is just pulling on the damn plies from top to bottom. Just here's a band, a clamp is here, it's here. They pull on it until you get this failure here. It tells you elongation and your ultimate tensile strength. So this is interesting. This is what I theorized, that the first manufacturer did it all in one layer. They're saying here that, yeah, that they figured that that might be a problem. So therefore, in an effort to mitigate wrinkling formation, because they believe the wrinkles is where the fracture happens, OceanGate limited build layers to 1 inch. Now, prior to autoclaving and curing. Now, this is kind of legit. The pressure chamber in Maryland that they used the testing, incidentally, I still can't verify if they actually went there, but they said they did. OceanGate said they did, and the NASA representative, when they asked about did they do any work for them, he's saying no, but keep in mind that's the NASA Center down, but he's representing NASA, but that's the one from Alabama. The pressure hull is in Maryland, but they'd asked him general question from NASA, and he didn't clarify that we don't do pressure testing here. It was more, he just said no. So I'm like, okay, well then you're owning the entire NASA response then, because that is the NASA representative. So the pressure vessel in Maryland, what they did, they made these rings. They say 5 rings also. I think it might have been three rings to band over the center one. And here's the pressure going outwards when they use pressure on this. Now these things are huge. It was made in Chester, Pennsylvania. They're huge steel bands like this. All right, how did they get it on there? And then when you let them go and make these taut right here, tight, as you see in the layers of the Titan, right? The Titan layers are pretty tight, but they're not tight like this, like the one I'm going to show you. But what they did was they heated the layers. They heated up each external tube until it expanded, and then the crane and track would slide over the the band below, and then they would get to position and stop the movement. As it's in the wintertime, they did it, and when it's cooled down, it shrank, and it made itself permanently bonded to the surface. When I say bonded, bonded. And now this is external pressure, the pressure vessel that I just mentioned. Internal pressure going outwards. So these are stirrups, basically, big giant steel stirrups over it. They're bands, and they go all the way down and they weld them up. And so the force is trying to break out of there. We'll have to break all these steel bands, and it just can't do it. And we're talking huge. Those doors are, I don't know, 2 foot thick, I think, something crazy. So this is awesome. We finally get the notification where the autoclave was done at Janik Industries. So you want to see the difference between where they did the winding in that location. You could figure how long it took, and the drive over. Did it loosen and shake and rattle and roll the position of the carbon fiber. Depending on the surface tension of the layers during transportation and how they moved it, sure, it could do that. It'd been nice if they'd have vacuumed it first and then transport it there for autoclaving. That would secure it, make it a lot more firm. Okay, so it's a 1 inch layers, as we already know that, nominal, meaning not exact, but close to 1 inch. Then they trimmed off the excess. The hull was manufactured with excess materials at either end, which is subsequently trimmed off. And I think it was much bigger than what they show. So sliding back to the top, electro impact is what I'm talking about. You find the difference between electro impact and the other company. And you see what they had to do to transport. The build sequence consisted of 2 cylindrical plies. All right, so hoops. Okay, here's a cylinder, right? Let's do that. Now let's go around it. So we're going to start, this is going to spin. All right, you can spin it that way if you want. And then over here is your pre-preg, your fiber on a spool. Comes out like a little spool here. It dips into a bath, and it comes out here. It's connected here, and then this rotates this direction. And this spool slides down just like a typewriter. Like that, all right? And you go to full length. Electro Impact uses a different one. They use one from the air from the Sky version, and it's beautiful. Their system is. It's not this low tech. This low tech one is what other people are showing on the channels. I no longer show that because I knew Electro Impact's product is much better. It goes from the air. It's like a giant. It's lovely. Hold on. Let's finish this before I might give you a picture of that, a video of that. The build sequence is real important here. 2 cylindrical plies. So 2 cylindrical plies. 1 and 2. All right. laid down with tension. That means they were pulling on it as they laid it down. But here's the thing, followed by one longitudinal ply laid down without tension. That's critical. So let's look at this. Let's look at the vessel like this. You know what? Let me grab the vessel. Now, let's do this. So here are the plies. All right, so they're going to come this way. All right, and they're going to be overlapping a bit. They're going to be, in an angle because you're going to overlap them. I just, for clarity for us, I'm just going to put them like this. All right, and they did two layers of these. So let's add another layer like next to it. So you can visualize another layer maybe next to it. All right. And then now, so here's the cylinder, but imagine it with only this, just going like this, just in that direction only. So you can see if pressure came in here at 6,000 psi, there's nothing stopping it from bending like this. There's nothing stopping that. But what they did was so grab green. Here they say laid without tension right here. So then they went this direction. It says one longitudinal ply. So every two layers, you see, there's another third layer. So let's just get rid of that. I don't want to confuse you. So for every 2 layers you see to the left here with the red and yellow, or whatever color you see it as, just one layer goes across it. All right, and they're screwed. It's not gappy like that. All right, but he only used 0.05 thickness, so this is really an issue for me. The band total width is that. So he had a custom made. Now this is a high strength ratio to it wanting. So in other words, here's a band, and I'm going to show you how strong this band is. It's friggin' amazing, the strength of it. And so any pressure now this pressure here trying to come down, it meets these bands, but these bands aren't continuously through their entire radius, as you may see. So the bands are if you could theorize or look at it, it's every third piece. Every third piece laid down is going across with one cross-sectional piece. That's this. So you get 1 layer, 2 layers, and then the other piece goes the other direction. So if you're going to find it in the profile, you'd go 1, 2, and then we'd be able to see this. It looks something like that, and then back to 1, 2, and then we would see the other direction. Or once you get to evaluating it, Materials Lab might be able to zoom in and get us that. So you could, as you make every inch up like that. So you remember we talked about the 1/3 inch scale, the 1/3 scale. The 1/3 scale wouldn't be the same because this is 133 layers. Is going to be behaved different than when you get down to 1/3. You might have 2 of these, let's say, and only 1 of these, and now you're loading it, whereas it's not equivalent. So 133, you might have equivalent of 1/3, so 30, 40 cross pieces. But in this piece, you might have the 1/3 scale. You might, by the time you get to that 0.33 of an inch, you might not have the ratio, the 40 to for every 90 plies. So here's the 133 in the background. Let me clean it up for you. So let's do that. So here's 133 plies. So if you do 133 divided by 3, you're going to come up with 33 plus 11. So 44 plies roughly. And then you balance it as what, 90? Almost 90. 89 plies. Let me do that right. So there's your 13, carry to 1. Yep. All right, so there we go. So 89 plies are going this direction, and 44 are going or support. So now we figure out the ratio of that, and you'll see the ratio of the 44 to 133, and that would have to be the scale in that 1/3 scale. If you're just doing it by inches, then you might screw it by the 1/3 inch. It might not make it. The ratio might be off. And so now you also have the issue of do you scale down the plies? Should the plies also now be 1/3 the size? 1/3 the size, because the small pressure chamber has large members relatively with their scale. They have these big 1/2-inch plies. The 1/2-inch 0.50 plies are put in the 1/3 scale. So if you use the same plies, and now you go to scale it up and make the bigger model, but you still use the same plies, well, you didn't scale it up. You didn't 3 times your size. This would be 1.5. So the answer to the guy that asked me is yes. The plies, the ribbon, the toe does matter. The toe size matters, and the toe, what we're going to reference it as, the toe size matter. They used 0.50, and I think they used it in their small scale. To scale it up, it would be 3 times the size of those also, and I believe that should be 3 times the size, and it would be 1.50. Not the same. It would be 3 times up. So they did here, and now there were no torsional plies. Remember I showed you that cross member, do some stuff like that? Nope, because Russ thought there's no torsional forces in the ocean, so there's no currents in the ocean, pushing at the side of the vessel, whatever. They don't exist. I'm being facetious. It says the sequence was repeated right here. We're getting into the details of it because this all matters. But what I'm going to show you in the image. Was repeated until 133 plies had been applied to produce a nominal. Nominal means not actual. It means close to 1 inch. All right. With the intermediate debulking, I told you that. That was probably taking it to get vacuum sealed. Vacuumed and also autoclaved. And then the dimensions changed to some degree. Now laying this untensioned, so laying this down without tension, this cross member. Now you load this, right? So you want to know how much these toes deflect. This toe deflects without tension. I mean, without so you pin it here and you pin it here, and say 9-foot piece of it. That's 9 foot or 8 foot, whatever the length of the sub is. And then you center load it, just see what it does. See how much, if you get deflection at all, just on it, period, on its own. Put strain gauges down here and see what happens if it's equally strained on each end. So you can put strain to see so basically you're putting a weight scale on this end, and think of it as just a crane weight. They look a little more sophisticated though. They look like that. And these strain gauges would be like, you put it on there. And then you load this with, say, whatever weight you wanted to. So you finally saw the deflection. Because remember, this is without tension. So this would just be laid down flat. However you plan on putting on the mandrel there. So you'd probably support this on a board that was flat. A piece of aluminum board, something that would keep this flat for fairness. And then you'd move it away. And you want to see if even the sag, even the sag gave you any number, any value. All right, the sag, the dead load of it. It'd be very small, so you need a very good scale for this. Very micro scale. And then you take it up. Now you'd want to take this to failure, just 1 strand. So you can extrapolate out from there at the full length that you're going to be putting it on. So 1 strand, you're going to load it until you figure out, oh, it's deflecting now. And then stop and go, you know what? What happens now if we put 2 strands on it? This is without epoxy now. Don't try to confuse it with epoxy yet. That epoxy is going to help. I want you to do this without epoxy. Since you're just laying it down there, lay it down without the epoxy first, and just figure out what we need to do for it to resist deflection. It might turn out you need to put 10 strands and secure 10 strands on top of each other, and then you could load 5,000 psi on top of this thing, and it gets no deflection. Now it's great, and you're like, oh shit, because that's the direction that he really needed to worry about. That's the unsupported span. Let's now double. Let's make this the submersible. Here's your end rings, your segments. All right. So the other direction is like this. But remember, it's on. They said no torsional plies. This is on an angle a bit, but it's very, very close. I really don't know what angle they used, but it's threaded really, really close, right? And they don't go back and up and down like that. I'm just trying to get you a sewing machine look. It's this machine, the machine they have at Electro Impact is beautiful. It would do it in the air also, not on the floor. It's mounted on the floor, but the spool is mounted in the air. Hopefully I won't forget to give it to you. So now we only have these plies I told you. Every 2 plies this direction, it's only supported by 1 of the cross plies. All right, 1 of the cross plies. So you do 2 layers, loop, loop, hoop around this thing, hoop around it twice. Once, twice, and then they tie it, and then you go 1 layer this way. All right, and I guess it's close together too also, the same deal. Then 1 layer. And then they go the other direction again. So once, twice, and then 1 more time. They go again the other direction. So there's a 2-to-1 ratio on this. So the span of the thickness of the 5 inches, there's a 5 inches here, right? So let's stay with me here. And yes, I'm keeping all the drawings up. All right, so there's 5 inches. 2-to-1 ratio. So we figure out this. Yep, I'm getting rid of them. We figure out the strand thickness. And now you can start figuring out the cross dimensions and the strand thickness. Hold on. So your strand thickness will be a literal. And you do the math yourself. There's your total. 0.9975 divided by what? 133. And give me a second on the calculator. So your strand thickness would be 0.0075 plus minus the glue. All right, you have to minus the glue between this. So it's going to be a lot less than the strand thickness is going to be less. You still get the same amount of strands. We still get the same inches, but I have to minus the glue thickness, which I don't know exactly what the glue thickness is. But when they lay the flat diversion this way, with the when they go horizontally down the tube, that's just laid flat without tension. So there's going to be more glue in that direction. So you can imagine with that, when they go to then turn around and go to hoop it this direction, it's under tension. You get glue bursting out of here, along with the glue that's down on this tension layer that you just added. And now you're getting this squishy layer, if you will. It's because this is now will be compressed. This layer here will be compressed by this. And then the glue locks it in, and now you've got yourself a compound system here, but it's like it's not post-tensioned, and it's not pre-tensioned. The pre-tensioned is the hoop part that goes around the outside, around the outside, around the outside. The longitudinal direction is not tensioned at all. It does have a squeeze on it, though, when this gets tensioned on it. So you'll keep track of that in your mind. So now you've got this, think of it as rebar placed there but also able to elongate. And I don't know what that elongation is. I did look at the studies on this, and they just did not study the product that they specified, the 0.5. That's not what they studied. So he made up his own bands, which are amazingly small. So some of this stuff I think I take for granted. You'll at least Google it, and like peel ply. Where is peel ply? 1 layer with the peel ply. All right, it's basically what it sounds like, doesn't it? It's your peel ply. It's your product that's sacrificial. It will wax paper basically. And then you're wrapping, your vacuum bag goes over top of that. You vacuum it, and then you autoclave it. That's basically what it sounds like. What it sounds like is what it is. All right, but I think doing there, some peel ply was still stuck, and that does happen into the epoxy embedded. You got to remove the peel ply, and then do your next layer. So think of this as a primer now. The winding curing. Let's see. I missed it by 1. Hold on. It's I'm reading it. The bottom sequence entail building 1 inch layers right here. Let me clean that up. 1 inch layer, and I'll tap over. Capping with a peel ply, which I told you what that is. It doesn't stay. curing the layer in an autoclave, removing the peel ply, and applying film adhesive to the freshly peeled surface. All right, after they get it cured, every time they decided it takes in the oven, then they use this applying a film adhesive. A film, it could be a spray. You break out the sprayer and you spray it on. It's a tack coat. All right, so it's a tack coat. So let's just do that word there. TACCOAT. That's why I'm doing it, for your tack coat. All right, you can hate me for TAC. All right, it's a tack coat. And the winding, then the winding, it's right here. And then you go back at it again. So the tack coat, it does matter. It's like sort of like doing contact cement. You know how you put contact cement on something, and if you put contact cement on the other side, and then you start binding the two together instantly, it doesn't work. You have to let it set. Well, the tack coat is the same thing. Whatever this adhesive is, he didn't identify what they're applying this film adhesive. They're not identifying it. You wouldn't really want to use dissimilar products, so it'd be kind of ideal if the tack coat is your same as your next binding agent, just so you don't have any chemical reactions that cause it to have issues. The winding, curing, and surface preparation process were then repeated until the hole was nominally 5 inches. Again, nominally doesn't mean exact, but what you say, like a 2x4 is really 1.5 inches by 2.5 inches, 3.5 inches. See the process illustrated in Figure 3B. Okay, he has it. Autoclave curing was performed at Janik Industries in Hamilton, Washington. So remember that. It says Hamilton, Washington. And the electro impact is here, a different location altogether. So you've got to think about that trouble of driving it across the property lines to just do that. This video is getting too long, and I got to show you a couple things, and then I'm going to end it. And this will take a long time, this series, to break it down to you. First, we're looking at the construction of it, but let me give you a nice little. Let me switch gears and give you something to enjoy to look at besides the technical part, which you'll need to know. I have to jump down to their external lab testing. So their external lab testing, they use ASTM 317122. This is not how the product was manufactured. Does not use this testing to verify their product. So they're using a testing process that's different than the manufacturer on this. But this is cured. So it's kind of a tough deal after the fact to be testing it. But you can see what it fails at, even though it's already gone through this explosive moment. The void percentage by volume, so they did a sample. They did multiple samples. And here's something, the compression tests were performed in a longitudinal direction on the samples that were machined from the piece of layer 1, so the first layer down below, inside layer, that was recovered from the ocean floor and examined as part of this report. The test specimens were approximately 1/2 inch in width and between, wow, hey, that's really some thin stuff. I think I had us down to 0.00. I said that our layers were 0.075. Well, they're down to, so for scale 0.0, they went up to 0.093. They went up in size. And also to 119. Okay, so their size is thicker. It says the long side of the specimen was aligned with the circumferential direction of the hull, Figure 50A. Oh, shit. I didn't want to get into figures and all. The results are shown in Table 2. All right, so it's right here. And then here's the problem. They use a finite element analysis performance on the Ocean Gate under contract, assumed all allowable compression strains. All right. So they used finite element modeling, which I really like real testing, real load testing. All right. Engineering's in the beginning in the 30s. Still, they rode out on that bridge themselves. They didn't just say, it's okay, and never show up until opening day, when the official opening day, ribbon cutting. Now it's otherwise now. All right, opposite. You're like, I'm not going on that bridge. You go out in there. All right, I'll come out in a month. All right, so the samples are here. Here's your samples after they did this different testing. And compression strain unavailable, it says. Here's the ASTM they used. That's the American standards. So you mechanical engineers know that. You can look this up also, that standard. But the problem is they used a product that doesn't use that as a testing method. So this testing method is interesting. So it's prescriptive. So this means that you don't have to use their method. You decided we're going to use my technique, meaning theirs. Remember, they have this here going on, the 1/2 inch bandwidth. Here we go, and it's this pre-preg. It's it can be squirrely like that. This one is twisted, so it's got twist. All right, and twist can elongate, and then the internal strain on a twist is less than the external strain on a twist. So imagine a cable. Imagine a cable here, single cable. Now I'm going to put post tension. I'm going to put six other cables around it, so a total of 7. I start pulling on this cable from one end. The one in the middle is straight, but these on the outside, they wrap around the cable, and so they're going to elongate differently. But they get tension on here. As you pull on it, these start pulling on the center one, putting tension on the center one, pressing on it, and it gives you the total value together acting as one. And when they pop, the outer bands pop, and it works their way in. I've seen many pop strands going from here. So this is Dr. Kramer here, the one we saw on the witness stand. This is the Dr. Kramer. But again, he's using his own test method, multiple test methods, meeting standards, these ASTM standards. I'm not totally on board with all the standards of testing, the methodology. I think a lot of it's defective, but that's just me. And it is just me. So this is the product that the doctor just showed us. They use the T800S. But this T800S, it also requires you use this epoxy here. It was not used. It was a different epoxy. So they were in their own zone at Ocean Gate. These are the standards that get you these results. In English, there it is. These are thousands. So 477,000 tensile strength with an asterisk, normalized at 60% fiber volume. All right, cured with this epoxy, this specific epoxy here. See it down the bottom? See, it's shit right there. So it matters, then they tested it. All right, so there's the and the cross-sectional area was 60% fiber, 40% glue, if you will. I'm sorry, this epoxy 2592, specifically at 130 degrees Celsius, and I don't know the timeline between that, and I don't know how many samples they did. When you deep dive into this stuff, sometimes they might only do 2 samples, and then they're like, okay, now let's run it. But they're constantly testing their materials. So they can stay because they certify them. All right, but this is the T800S. This is the one they were supposed to be using, the Toray, and they're the dimensions of it. The typical bobbin size in millimeters, and it's much larger than a 1/2 inch. All of these in millimeters to inches are significantly larger than, and here are the measurements over your correlation over here. So significant, not one number is under 1/2 inch there. Not one of those numbers, from millimeters to inches, not one. Now, I don't know which one they use, the 12,000 or the 24K product. But there's the size, and they didn't do it. Remember, they had it cut down to their own version. It's craziness. Now I'll give you a little, the fun part, the treats. So this is the top side. It's just field cut. So they field cut, probably that means it was cut on the boat, on the ship, right? Maybe it was cut underwater. I don't know. They said field cut. There's two versions of that. One's on the ship, one's on the boat. I mean, one's down low. Yeah, I don't know if the machine had a capability of hooking a saw to it, but I bet you they wouldn't have to add water to it to start cutting the hydraulics on that. All right, so this says fractured end to your left. Now, I've let this sit with me for a while, and I'm going to give you some awesome stuff here. This is the same piece as it says. It says inner surface, and there's the field cut. All right, and there you see it. There's the striations on the wall, the interactions. Any two materials that contact each other always trade off. You knock on a door, you just trade it off. Part of your flesh on the door. A piece of metal hitting a piece of metal. Metal is traded. There's always a trade-off. So microscopically, he can look at all of this, and if there's any material left after coming out of the water, he can figure out if the titanium ring even rubbed against this. All right, it'll be a trade-off onto the titanium ring. But damn if that titanium ring doesn't look like it was scrubbed. The end is really beautiful. Look at that. That's where I believe the titanium interface ring went all the way into here. So this piece did not fail. It did not fail. It did not fracture down the middle. How do we know? You see no fracture. So when you triangulate this back end, you start putting pieces back together, it didn't fail. Look at the opposing end, didn't fail. So we can pick the two opposite ends as a failing layer. Now this is layer, didn't identify the layer. Hold on. This is outer surface. All right, let me tell you the way this works. Let me cut to the chase a bit. Here's 5 layers. All right, that's the way it would look like, but count this as a layer here also. And they come all the way around, all right? I'm just going to do that, and I'm doing different colors for a reason. Here's our penetration, and there's our penetration. Let's do this. Backing that up. I'm going to exaggerate and ramp back up. So our penetrations, you see it can push one layer. Think about what I just said. Can it push one layer? No, it can't. It has to push all the layers. See how I've got that one layer bent out? No, because it's connected here, 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 and here. So for this to do that, it would be a mirrored through all layers. You'll see this. Through every layer, you'll see this. A fracture that will line up. That's your beginning of your failure also. All right? Then everything else can be multiple buckles, different way, depending on how the pressure then changed. It started buckling it. And during buckling, as it came in, buckling from front to back, the piston action, this top layer, this number 5 and number 4, I'm going to show you what happened to them. It peeled off. It said goodbye. It peeled off. It blew off. It peeled off and came to rest wherever it came off. Like this is number figure A. So he identifies that up here, doesn't he? Let me look for it. So let's cut to the chase here. And there we go. The Deep Ocean Test Facility in Annapolis, Maryland, between February 25th and March 4th to a maximum depth of 4,200 meters. So there's our testing facility that's acknowledged now. So when they asked him, was it pressure tested, and they didn't do anything, he said no, but he was referring to Alabama, their witness. So now we have that validation from the images I showed you yesterday. It's posting tomorrow, so this is yesterday. Or posting later. All right, and the March 4th to a maximum of 4,200 meters. According to analysis performed under contract for OceanGate, the test depth was limited to the material properties of CB grade 3 titanium in the vicinity of the viewport. The Titan had completed 17 dives below 1,300 meters prior to this mishap. All right, but I don't know what they're jumping there. They're jumping over there. The hull was subsequently tested at the Deep Ocean Test Facilities in Maryland. That's the one I showed you with that metal band thing. February 25th, and he came in at March 4th to a maximum depth of 1,400 meters. Just so you guys know, there's only 365 days in a year besides leap year, and the they don't let anybody use this facility. You've got to show that you're doing something groundbreaking, if you will. And this carbon fiber met that rule. I think you applied to University of Penn, or is it Penn State, to be able to get access to this government facility. I think they manage it or something like that. But there it is there. They did get there. So this is interesting for Zachary. After the first hull failed, they cleaned up the rings, the segments, by machining. So unless they were super accurate, they took away more value, more material. Nevertheless, they then go to testing. It says, according to a former director with a written Ocean Gate process specification, the segments and hull surfaces were prepared for bonding by degreasing with MEK and roughly with stearate-free. This is the damn sandpaper, all right? Sandpaper, yeah. Contact angle measurements were taken between the steps to ensure active non-contamination. Surfaces and particles were blown away using filtered shop air. Tested by contact angle to ensure it did not introduce contamination. The adhesive was mixed and applied to both the segment and the hull surface. The hull was then inserted into the C channel. That would be the bottom one. Aft joint was formed by lowering the hull down into the segment, and forward joint was formed by lowering the segment down onto the hull. So when we see that sky view image of it, and it's coming down, that's the window, the port. The window section, rather. The entire assembly oriented vertically, as we saw. Spaces within the joint controlled the bond line thickness. Okay. Spacers. They put spacers in there to make sure that the hull was subsequently pressure tested. Then they went to Annapolis, Maryland, all right, and got down to 4,200 meters, and I don't know how long it stayed there. They don't release the testing. And we know about this real-time monitoring system, which we apparently don't know exactly where. That's not been verified. I'll give them an A for this report. It came out in July. It was pretty soon, and yet so they jumped on this report. So that piece is so critical for us because this is where their testing comes from. It says, at the viewing, meaning when they went to see everything, the pieces, they decided this piece would be the most critical piece they want to use. A piece of carbon fiber composite hull was identified for laboratory examination in accordance with the U.S. Coast Guard. The piece was transported to an examination at the NTSB-2 laboratories and is shown in figures 1A through 1D. The piece was recovered from the ocean floor approximately 300 feet from the main wreckage, which consisted of the aft dome, aft segment, aft hull fragments. As shown in figure 1E, it measured approximately 61 inches by 20 inches by 1 inch. The other surface was coated by a green film adhesive, and the inner surface was coated with a white paint. One end was machined, and some bits of cured adhesive were still attached. The other ends, this is the piece we're going to look at, the other ends, edges are fractured. The piece was examined to characterize the structure and properties of the composite hull, materials, adhesive bonding, and to determine where possibly the modes of separation. All right, so there we have that. And then they bought additional hull pieces. So we got one end that is good, the other end so-so. So this is their home run piece right here. This is the piece they chose. This is 1A. Hey, Max. Yeah. So this to the left, you see that's the fractured end. To the right, they call this the machined end. And there's the longitudinal version. This would be how they can find those bands. Those are the lax ones. The laxed, meaning not tensioned. And as you just said, they said painted surface underneath, and we see that the paint's been impacted. All right, so during this implosion, this is the inner part, the inner liner, number one. It didn't escape. a lot of brushing, a lot of impact. So now we know this can't brush itself. All right, but the floor could do it. The floor coming across could do it. The metal liner could also do a lot of this, but we have multiple directions. All right, let's just map these directions a bit. Here we just got, we got multiple directions there. We got some here. We got some here. It was like it was thrown into a washing machine before it was ejected out. Look at the scratches. We got some here. I'm not sure whether I'm going to count this one or not. I'm going to get rid of that. So you can see that, and you can see where they start. You would even better say, well, one piece drug itself there. You'd be able to see the start and finish of it. You could really go into this piece alone really hard and try to figure out what pieces traded love with it. What pieces kissed up. All right, so here's it looks like this is presented as the same piece. And we have the fractured ends. All right, so this looks bonded. And then we got this fractured end tapered off like this. And that's that part I'm telling you about, how you could get water under here, water pressure under here, and bend this up, fold this up, and you would get a nice clean break like that. Remember this hoop, it's hooped, so it's only going to have the resistance with that a couple of bands here going down through the layer. So going here, there's only going to be, what I determined, 40 of them, 44 cross pieces, and they're in that direction, so they'll break free. They won't help. So the only thing stopping it is the bands going in the hoop direction, and they can easily be fractured also. Let's just do it like this. That's no problem for them fracturing that direction. So now we're looking at that's the piece watch down there in the Netherlands. It's down there. And this is that machined end, as they stated. Is that right? To the right is a machined end, and this has that tag on it. That's the fractured end, as they call the fractured end. It looks pretty clean to me. So there's that tag. So this is the piece as they came upon it, as is revealed to us. So it looks like when it came in, this is the bottom shell, that this piece, the implosion was from the top. Let's say it was from the top, and this was the bottom. This is the white bottom of it. It pushes out. It fractures that outer interface, that outer ring. So here's the interface ring. This gets fractured. It pushes this outwards, and it ejects it off. So you're no longer part of the party. You can have go have a nice life. But as it's going, the end cap the end is also coming in. And as it's coming in, it helps drag across the bottom of it. Remember the white part, how it's torn apart. And it possibly pushes this in this direction across the back of the ring, the top of the other ring, the rear ring. And I need to know the real field, the layout of this in the field, and I can tell you that. I can map it even better. So this plunges this down. It's such a great impact that it buckles it right there. But remember, the hoops go that direction, so there's nothing to stop it from buckling that besides those few cross members in here that are every three courses. So it's an easy home run for it to eject it off. So it ejects it off, no problem. All right. And I don't think it, just so you know, so that piece we're looking for is not here. This would have been in the way, and that piece, the back of that part would have shown it. It's not on the other side. And there's a band up top of here too, down the middle here. So I don't think it's there either. And I think there might be one in the bottom also. For the turntable, for the weights. So as you see here, we don't see any striations here. We don't see the material missing, the coloration. This still gets the liner on it though. If this is the outside piece, it still needs a liner, but this doesn't make sense, that color. the color should still be, it should be gray. Why do you just have this blue on it? So I don't, that white, where's the white? It's white, it's the same piece. Okay, so it looks like that. It's not, it's okay, it's fair game. It just looks, the coloration is wrong. But here's the coloration corrected here. And then I think, what are you smelling for, Biscuit Head? That's my, you smelling my feet. I took a bath. Max, I took a bath. It's good smelling feet. All right. So remember, when you look in this here, these bands, every third one is a different direction. We can't tell with our magnification here. And it looks pretty good. I mean, they look, you know, if we're looking at these, let's be magnified a bit. If we're looking at the gaps between each one of these. All right, so I let the chips fall where they fall. So if it looks good, it looks good. As you look down here, you count, look at the white lines as the glue. And if you look at that spacing, oh, this is the sample. It looks great. Now here's a little bit of buckling here, which they, right there with when they laid the fabric down, there's something got in a little wave. It could have been a machine bumped or something like that. You know, a little stop, you know, until they had to smack the machine and get it aligned again. But it's repeating itself right there. Yeah, it could screw up one wave and then continue it. All right, this is a sample, so we're back to that again. Let's move on. This is just that process of curing. We don't care about this. This is nothing. I want to show you the sample. So here again, there's a test piece there, the sample piece they took out. And this is what it looks like here. And they noted, which they're glad they noted it anyway, periodic light and dark. They just wanted to, you know, it's data. And here we see that we have a shear plane there, right? Pressure is there. The way it acted. Now to the left, it went up. The pressure is, I'm gonna circle it. It's on that upper layer, pushing down on these two layers, which then separates here. So it looks like that. Then pull it away. So that literally is that piece there. Now if this could bend down right there, meaning right here really, then you could bend it down and fracture those and get this piece trying to act like a cantilever trying to support the two pieces above. It can't, and it splits back to this point here. I'll move it away so you can see it. All right, so every piece has a story to tell. Same thing with here, except for we don't have this. So this would have been a piece in here that had pressure on it. It pushed down. It acted like a pry bar. It split. It went back to here rather. The forces out here were there. It pushed down on it. This bent down, if you will. See it? See that indicator back there? That's where it bent down. And it broke its way into the future. All right, broke its way into this YouTube channel. Now this is, I don't know if this is the real layers of that or not. So, yep, that is the real layers. That's the real deal. I'm not worried about this scrim. All right, so I'm not worried about that. I'm gonna go on. Yeah, I'm not getting too crazy about that this time. And we know this, this is about the voids right here. And it's going to be voids. And that void could be that longitudinal piece, right? Remember the longitudinal piece they do relaxed? So one piece longitudinal. Then what do we have? 1, 2. Oh, wait a minute. 1, 2. Oh, I see what we're seeing now. You see how I play it like Columbo? 1, 2, and then you put the... So what do you see? That's their longitudinal piece. That's the piece that goes along. I know it's been a long video to get to this, but this is what it looks like. So this is your hoop, and then that longitudinal piece. All right, and then longitudinal piece. Now, this is, I don't know if is it a sample? Higher magnification cross-section images showing the variation in porosity and the inner ply resin layers, plies 122 through 126, applies 2 through 7. So they did 2 samples. So 2 through 7 is the bottom one, implies 122 through 126. So let's see how that works out. So that would be, I see another ply down there. So that's hoop. So let's do H, H, and then longitudinal, H, H, and then longitudinal. What the fuck? It says it right there. I thought I was breaking it down. This guy is good. Not me. The guy that did the report. I didn't even see the longitudinal. I do this for you guys like this so you can get it in my brain as I do it. And then I can adjust it later. But you're getting my processor now. I don't have a script I work from. I don't need a script. I know what I'm looking at. It's not like the other channels that need scripts. That's why I can challenge any engineer to say, let's go head to head in a live broadcast and talk about any of these subjects. Right now, I'm still a virgin with this, with the data here. So I'm still processing it. But I welcome the interaction. But at some point, I'm going to be, way beyond any of their level. So I'll take the challenge now, but, what's the point of us challenge each other right now when we don't have all the data? And I'm not talking about the witness statement. I'm talking about the structural behavior of this. The witness positions just seem like they all were complicit. And if you're complicit, it sounds like you might have a little conspiracy going on there. You knew this, knew that, still continued. You knew the danger it was creating and everything. So, sound like you might be part of some negligent homicide shit. But then they got that waiver, so the waiver is the waiver. Some crazy shit. I thought I was breaking it down. There it was. So you heard it live, not rehearsed. All right. So let's see what he has here. Oh, he broke up that piece. It was shadow. This is that shaded piece he talked about a second ago. And now he's looking down here at the block. This the pieces, 2-inch, usually like 2-inch squares samples. But these are a little less. These are 1 3/4, roughly. Oh shit! He found the longitudinal piece. Oh no shit! Look. So there it is. There. This is the one that goes out. It looks tight. It looks like, so that would have been one of the bands that work its way around. Remember, for 1, then there's 2. For every one of these, there's 2 layers going on top. Even though we can't tell if this is 2 layers or not, he doesn't say that to us. But this would be the equivalent of the density of it. And it, tell you what, that sumbitch looks nice. I'm not worried about the abrasions and all that. Yeah, this is the outer. I think this is the outer. Remember we saw some sanding going on? I'm looking at the porosity as you talk about. Look at the one to the right. I mean, look at the layers just in general. Don't, if you can get rid of your bias of hating and just treat everything separate. You can hate when you have to hate and don't hate when you don't. That's pretty consistent. I don't see in this sample where we ground down at all. I see they look, consider the circumference, they look parallel. Looks like they did a great job there. And then this one looks, the top view, where they had to clean, obviously they had a machine to clean the glue off, do something to clean this glue off. But even cleaning the glue off with their process, they revealed, I'm thinking about how the hell they clean the glue off without creating their own striations, their own texture here. So I find this maybe defective thinking on my part. Because I don't, that glue, how did they remove it? You use a power washer, and then what? You created this texture? How did you control that you didn't introduce striations yourself? Well, looking at the density, it looks great. But again, if they use a sander, you're creating you sanded. You created this density, this appearance of density. So the ones to the right, though, this is not sanded. So I can use that one, and it looks great. And you look at the top, you see there what they were crying about, the spalled scrim exposure. Oh, that's that layer. So this appears they did sand this. I think, what did they say? Oblique cut. Yeah, so they did try to remove some material to get us a look at the think of you guys body shops, how you taper off, feather off. It's basically what they did here, so they can reveal the detail of it. And it does look like they went that direction to originally prep it, and this is the true. It appears that's the direction of it. Let's it's pretty damn dense. They'd have to magnify that so we can see that and slide across a magnifier to determine that. I mean, come on, we're not building a clock here. They can't get, this is nothing. I'm not upset about that. It didn't fail there anyway. We see it's not broken there, so there is no failure right there where they're saying voids. They're talking about fit and finish, basically. But there is no failure there. All right, remember, this is glossy resin. Okay. So glossy usually would indicate, it's not glossy regions. Well, there is no rubbing, as he would say, if it's glossy. And then again, rubbing could create glossy. And what does he say? Rubbed appearance near right side glossy regions and voids. How about people saying it's so much heat? Well, we're looking at the resin, right? So the resin bakes in at whatever, 130 degrees, 130 Celsius rather, whatever that original product was. This one, I don't know. You can determine if it was anything burned, and you can determine the heat. Did you see any burning? Any indicating that it exceeded the heat of the friction layers when they failed? Do we see any burning? Any melted or fused type glue? So that can determine temperature at the time. People think it's great temperature was created. Okay, so there's that piece again, and I talked to you about how we get this there. We also can get this from water pressure coming up and lifting this up, and then it would get under there, lift, get back to here, and stop right about there. But I like my other cantilever version of it where it's here. Oh no, this is the other way. So see, I just turned up. See, it's like this. So no, this would have been this piece. So we just do a continuation of this piece. All right. Let's just continue it down like this. Okay. And then the next layer also. And then continue that layer down. Now the water gets under there, the force rotating it up. Pop flakes off this section, and when it finally comes up to this position, it severs this position. It severs right there where you last see it at, last known position. See it right there. That's the last known position of that bottom piece, 1-inch piece. So this automatically details that it went up. So the force that did that was up. Now, could it have been impact on the beach? I doubt it. I think this is it would probably be more flexible at that point, bouncing. It's kinetic energy. It's going to be absorbed by the sand. So I doubt it. This does look like that segment. There's that little piece there. So it looks like that end. Now with this one, the same thing again. So you see that this will be continuous. All right. So how do we get that there? Well, I rotate it up. Rotate it up to a point where it then looks like there. See the position of it? And this top part flakes off. All right. It goes off to wherever it goes to. But this bonding action still controlled it. This back here, I can't. This might be water pressured under there. They made it back to split it. But this is going to be a downward force on this delamination. So this bottom piece, somehow, if it continues over, this is a downward force to push it down. And the hinge is here, way back to there. And the break is there. But you see the hinge is here on this one. So it was continuation there, right? Going around. Force is up. And the release point is literally at this angle. Literally, that's the angle it releases. It breaks. It fractures. Remember, they're just a bunch of individual strands that are held together by glue. And here it is again. This would be this one. And it broke here. And it was very close to breaking there when this broke first. And if we see that this piece acted like a spring. It's back down now. But this piece to break was probably up here like this. And this piece was probably flexed way up here like that. Way up there, like it was probably flexed that far up before. And this piece, this delamination they call it, this was pried down. Okay, let's move on. There's my layers again. So now we're looking at 1, 2, 1, 2, 3, 1, 2, 3. So 1, 2. So we have our hoop that goes around the outside like the song, and that's the glue. Glue looks tight there, doesn't it? And then this is our longitudinal piece, and then pretty tight there. So this piece looks great. You know, down the bottom there, you can argue all you want, but it's not broken apart. The void's there, but it's not broken apart. So even under compression, I don't see an issue. Now let's think about that real-time monitoring system. Could it be hearing these things close up and down? Well, we don't have any indicator that's broken free, so delamination, so no. Okay, what's he got here? I like his angle of incidence. So this guy's pretty good. Young he seems young, but he's pretty good. He's looking at angle of incidence here on this. I'm trying to look at it first before I read this down below. So 43 and 48. Yeah, I think this guy's going to do a fucking awesome report if he puts together his data. It says 45 degree slant cracks at the heaves of a top layer. So this could be from one action. There's this tube around here. And let's put this right here. Let's put the, here's 45 and put the other one over here. That's this direction up. So you push up and you can create these fractures. All right, let's do that. And put the bend over, put it back in there like that. As you push up, this could be 1 and 2. This would be the compression point then. Both of them would be compression causing a little shear. But I don't see that. I see that the different elevations. I'm not. His lines are kind of in the way for me to read it. They are in the way for me to fully read it, but it looks like the tolerances of glue. I think, yeah, and this one I think you just might be seeing ghost, I call it, where you just see something that's not there. Yeah, I think it's pretty tight. I think that's within the tolerance, because I don't see any break at the bottom. All right, it looks pretty bonded there. And if he's implying that it's moved, or is he implying it's a cold joint? Okay, let's see what it says. Now he calls them cracks. A top layer 1. So this is the glue. He's saying top layer 1, so layer 2 goes on top. So this would be a cold joint then. But the crack would be our noise also. But I don't see grinding there. I don't see it. It would be, you know, the compression. Remember, it works all the rings. You can't just, from the pressure outside, you can't just push on a single layer. It's pushing on all of them. And they think of it as segments like that. And then another segment. I did a video like this already. Just think of them as a bunch of individual segments. One inch segments if you think the entire hull, to make it easy to do your PSI. And that would translate to, you know, more surface area, different surface areas. And this, ultimately, this smaller inner surface area is getting the most PSI, if any at all, if it does make it down that far in pressure to the inner hull. And you wouldn't know that unless you made it 4 layers thick, leaving the inner layer out. So you would test doing 4 layers, all right? 1, 2, 3, 4, all right? And then you can use a 5th layer. And you put a caliper in there inside, and you pressure test it. And if your calipers, you know, like that, right? And you got the pressure chamber in there. If they squeeze and get closer together, well, then now you know that your chamber is not thick enough. It's suffering under compression. So you would check that in the middle, the midspan. At the edges, it's going to be stronger. So you check that at the midspan. I'm trying to wrap up the video for you. Let me see if I can race through some more images. You learned a lot about that. These are just, these hackles just give me the hackles. I don't even like looking at them. Some things give me like the heebie-jeebies. That does. A lot of things don't. That does. Longitudinal rubs. Interesting. Are they trying to imply that, now that we have different data, are they implying that the cross members that rub these? All right? Because there's only 1 layer of longitudinal material. So it can't rub itself. It can, in theory, though, at the overlaps. So where they overlap, because they got to overlap, but just a little bit. And this is under, the scale here is just crazy. It's 100 microns. It's a very small scale. I mean, yeah, to look at it. And this is 20 microns. So they magnified it and made it 20 microns. Because believe me, that scale to your left, yeah, what's the scale, 20 microns? Yeah, they magnified it. Oh, yeah, there it is, magnification. Yeah, see, this is see, it matters. So this is 350x magnification. When you start seeing details like this, you're way up in magnification. And it's 2000x. And then this is a 20 micron scale. So this rubbing is somewhere about 5 microns. Enough, you can wear the mask, N95 mask version, basically, which is really 5 microns. All right, this is again 1000x, the scale. The angle of view is 13.75 millimeters, which is nice. This is by NIST. Okay, electron microscope. Additional longitudinal rubber arcs. Okay, not going to worry about that. Nope. It's the pieces that matter. The large pieces are going to tell where it fractured. All right, I think I did a short version of that. I didn't give you the video yet. We went over that one. These are samples. I could care less about them at this time for our video content. Nope. This one we went over the layers. When he's referring about interface, that's the bonding layer that, they remember this film they said they used, and then they added. So this is what he means by interface. It's from one layer to the next. And what does this say? Longitudinal cross section. Oh, this is better. With layers and interface labeled, and the other thing. Okay, you said interface is labeled. I wish you had a better image of that. Oh, this is the one that's not damaged. So it's a drip. It's a drip. I was wondering what this was right here. I'm thinking in my own mind. That looks like it's duplicated there. What the hell's the magnification of this? So that is 1 foot. Standard, I don't know if they use a 50 millimeter lens or not. They should tell us what lens they used. So that's kind of wavy, isn't it? Voids and adhesive layer. Yeah. Now, remember, that's going to just close down, though. But you do have to, and that's going to be a noise with the damn machine, with this is pretty voided. That's pretty nasty. So remember, they had a transport. My guess is that the layers went down great, and that's their interface ring. Interface, I think, where they go from one layer to the next. So that interface sucks. So what, did it take too long to press down the next layer and squeeze it in place? If we look at this, I think what you're looking... Oh, this is fucking... This guy just reading my mind. It's just killing me here. All right, so it'll be 1, 2, 1, 2. So this is longitudinal. All right, these are longitudinal, and these two in here are the hoops. And then there's glue between them. I said the guy's killing me because every time I try to reveal something, actually, no, I think he reveals it already. But he doesn't identify this. This is the interface from the 1 inch to, say, to the 2nd inch. Oh, it says right there. From layer 3 to layer 4, but he doesn't identify this. This is that maybe he does. Hold on. Closer image in the adhesive between layers 3 and 4 shows voids of the layers 3 and 4 adhesive interface. Yep, He identifies it there. I'm like, hold on, this guy doesn't miss a fucking thing so far. There it is. There it is. He's doing great. So that's pretty damn squeaky, right? That shows you that something went on there. You know, did they go to lunch and come back and say, okay, let's pick up where you left off? That's just craziness. But looking at the parallel of all these different directions, they look parallel as shit. Besides maybe a wave here. But remember, this is going down without tension. So these guys, if you notice, this is without tension. The others are with tension. So if you look at if we could figure out the thickness of this, we would see how much we would see. So what I'm doing now is, these were the tension pieces. This was just laid down without tension. If we could measure it, we would see how much tension applied. So we would measure calipers here to here, and then calipers from here to here, and then here to here, and we could see if the tension is equally tensioned throughout the entire sample we're looking at. Now just using my eyes, I'm over here right now trying to pick out a section and I'm moving around. You know, and then stepping back of my eyes, it seems like this is pretty fat. All right. It seems like it's pretty thin. So I would say that one, even though he laid it down, that one received tension in it. Look how thin it looks. And that's the one that stops that from this way, the loading from that direction, from the outside, from the ocean, pressing against this. This is the ocean up here pressing down. These are the ones that resist the ocean. This is fucking huge fat. How fat that one is. That's 2 fucking layers. No way is that a single layer. No way is that a single layer. So they put 2 layers there. Let's see if that's duplicated on the different layers. If they duplicate that on another layer. There's layer 4. That's 2 layers. This one's maybe even fractured, but this is 2. This is really funky. It even had a different coloration. This one. This one. This area here. If you're talking about coloration, now we can start talking about coloration and what it might indicate something. That one looks doubled. I want to go back to that double one. This one. Okay. So this is, remember, the load's coming from here, ocean to down. So this will be resisting that load that way. This one's in a different position. Oh, wow. The coloration of those is so different. And here they are here. Oh, no, he didn't quite point it. He just said longitudinal direction. He wasn't identifying the exact strand, so I still get my my flex. See the arrow just pointing there in general? It just happened to be on the one that time. Post hoc. Procta ad hoc. You guys can look it up. It means just because of one thing doesn't mean it's tied to the other. So when he says longitudinal direction, there it is again, just placed randomly. It just happens to hit the line here, and then here it doesn't hit at all. So that would drive me crazy, just drawing that line he just did. For a report like this, is wild there, and then this one's on the string here. That would not be tolerated by myself. And I would argue the same thing with this. It's cockeyed. It's twisted. All right, so remember, the ocean pressure is this way, and now let's look at these lines. Just put your head back away from the video, and then you look at the lines. That's the part that's resisting all the way layers down. Remember, the outer surface area is getting the most pressure. The next one is experiencing more pressure because that outer pressure has to go through that layer. But is it experiencing more pressure? I don't know. Not without a gauge, I wouldn't tell. I don't know how much it's deflecting. How much did this reduce the pressure from the next ring in? In theory, the smaller ball in the inside has the most pressure from all of the pressure outside. But it's getting reduced by all these multiples of longitudinal directional post-tension, including epoxies. It's reducing the load on the inner theoretically in the inner ball, if you will, which would be the inner circle. Oh, good. We got a beautiful piece here. And is this the full piece? Let's see what he says. It says, it's a cross-section of trimmed end piece of the first full-scale Titan hull. So this is number one. And they didn't use that doesn't even matter. The first full-scale, because this one imploded. So what does that matter to us? That's whoa. Yeah, well, that's why it imploded. That guy didn't do any Spencer composites. He just did it all one-off. And so you can imagine this wouldn't, it'd have a problem with autoclaving, baking this all together. And you can't make the heat, can't get the compression in there to make the glue bond. You can't get the compression. Although I don't know exactly how he compressed it. So I can see why he wouldn't go back to Spencer. And there's the one I told you. Wait a minute, which number is this? What is this one? Images of the centerline, delamination, and the full-scale Titan hull trimmed end. All right, so what's the magnification of that? Though it says 2 inches there on the scale. That looks like shit. Is that the, it says the Titan. Maybe that's the first one again, which I don't care about. I just want the debris field. So let's go back. Let's go find our debris field. So I talked about that this thing went in, it spun out. I talked about it for you newcomers. I said this thing spun over a year ago, I think it was. I'll get it to you. And I used a Lysol can to identify it, to show that spin. All right, let me pause it and come back to you. So a piece like this, you'd have to climb in. You'd have to climb close to it, get in there and take a look at it to try to identify how each piece is splintered, and you would map it. And then you would determine, okay, this little splinter's up. So this could be pushed down. This could be the downward force, and it could be a downward force over here. And so it butterflies in like that. So this is a downward force, that's a downward force, and the failure's there. But you'd have to come up with a reason why that section why this is weak, this part, and you would have to find it here. And something like, I understand they put screws in the damn hull, which you're not supposed to do. I want to get you to the back of the hull again, and I'm going to show you how something, I know it's late in the video. My gosh, so much for 20 minutes. The back of the hull, and I want to show you the, they're testing multiple layers. As you could tell now that you're educated, you could look at this and go 1, 2, 1, 2, 1, 2. So you'd say that's a longitudinal one, going along the length 1, 2, 3, 4, 5. So it's 5 longitudinal pieces, and then you would go there's 2, 4, 6, 8, 10, and 10. So this is 1 to 5. This is a 50% ratio. Their test piece. If this test piece, so it's not real world. The real world, it would be 1 to 3 ratio. Remember, 2 one direction, 1 the other. So the sample, considering it's a sample that they tested, I would say it's not a fair sample. Let's do it again. So on the longitudinal, that's 1, 2, 3, 4, 5. And there's 6. There's the bottom piece. So there should be 6 times 2. There should be 12 of the hoop direction. So 2, 4, 6, 8, on count 10. See, left on that bottom piece. If you'd taken off that bottom piece, that would reduce this to 5. And now we'd go 5 times 2. We would just need 10, and we would make it. It would be 2, 4, 6, 8, 10. That bottom piece left on, or the top one, whichever one you want to pick your poison on, throws this testing ratio scale off. So it's the details that count, right? It's the fine details that count. Here is the compression specimen, and this is what happens under compression, how it fails. it displaced. They put obviously they put a shape like that into it, V shape. They press down, and at some point they wait for it to fracture, and it fractured abruptly. It gets you to this position, I think. This place displaced, or they bent it on the ends. Let's see, compression. It'd be weird how they test this. This is very weird because it could be loading from here even, and that would be so amazing if it just broke out that V shape down there. I just discussing it with you, but I don't know. They're not revealing what their test is. Let's see if they no. Compression specimen and B shear. Okay, so that's a shear test, and this was the compression one. What? Yeah, they used so they didn't. This is not a 10. They use this in shear, and this one they push the sides together, and this being so strong with the extra piece in it, and this would be, I don't know how long the piece is total, but it was more strong in this area here. The bond over here was so strong. It was probably the same bond all the way through, but this, when they were driving it, the middle part, that this would be a buckle then, the middle part that buckled, and it looks like this, that it still had strength like this, and it acted like a spear. And it literally just, so that would be the shear plane here. It fractured in a shear action, pushing it in. Now, I don't think it's the piece right there. No, it's not. And this bottom one is a shear, and I don't know how they sheared it, but so this is we can't, this is probably back, and this is forward of us. So we look here. It's like it's one hand in front of the other. So your left hand is closer to your face than your right hand type thing. And I don't know how oh, that's the end of the paper. Good. So back to this image. This is the bottom is, so this is the bottom here, see? And the top of this dome is here. That would be the better version of it. So the bottom here should be over here. This indicates that spiral I talked about during the failure. Now, where's my piece that I want to show you? I think it's, so there's the tank. I already talked about that. They had one labeled here. Hold on, let me find it. Okay, this is a beautiful piece here. So this is this is looking from the back side of the dome at the seabed. All right, there's that piece there. All right, so keep track of that in your brain there. And let's go back to it. That's the bottom, as it states. All right, so you, right here, this says bottom. So we're looking from this direction now. Hull piece C. So we come back to it. So they now call it C, layer 5, layer 4. All right, so 5 and 4. And then over to your right here is that piece. Now, I'm going to Columbo on you now and let you figure this out before I say it. I'm going to give you a bunch of hints and walk you into it, up to it. This is the interface ring. This was connected to here, but it was clocked down at the bottom, right? So this is that tab I talked to you about, where it's more like at the parallel with the floor. It's a little different. It's tab is like right here, and then this bottom piece is right here. So this tab is here now, so this got to rotate all the way around. But now I'm going to walk you into it now. See that 4 and 5? What do you observe? Well, for layer 4 and 5 are the top layers, right? So layer 5 and layer 4. Let's do it like this. Okay, and let's do it like this. And here's the interface ring. This is this ring here, the segment here. And it comes all the way down here to layer 1, 2, and this is 3. And so here's our ring. Interface, let me just do this like this, all right? So what happened? Look at this thing. It's behind. Here's this the hull of the vessel. So this is layer 5 right here, and layer 4 is underneath of it. These two layers here. I'm going to change the coloration for you. They're combined together, and we'll do that for our clarity. And there's the interface ring. It butted up to the interface ring. This butts up to the interface ring on the other side. Have you caught on yet? It's behind it now. There's the interface ring on this side. Here's where the interface ring was. This was here. During that spiraling action, that spinning action, and it was still compressing in from each end. Each end was being driven in by the forces of the water trying to press these together. At some point, layer 3, 2, and 1 separate from layer 4 and 5. Layer 4 and 5 make it, during this spiral action, make it into the back of this chamber here, help push it off along with the bottles, and it drives itself, and this would probably be near the, so here's the bottom. Let's clean this up a bit. Here's the bottom. This probably would not be where it is. It's to where the tanks are. It's probably the bottom. So as you see the tank there? And so it drove itself in with the tank. Layers 4 and 5 dropped down. Layers 4 and 5. 5 and 4 drop down from their position way out here at the top. They're on the outside here at the top. The outer surface is layer 5. The layer below that is 4. If anything, you would think like 1, 2, and 3 would be inside here, right? But no, this shows you that how this buckled and came in. It positioned 4, layer 4, and layer 5 inside the vessel, spinning it where it spun around, allowed the water pressure to reduce by coming out this outside here. And you can see that the tank got compressed. It really helped reduce the compression, the cylinder action. It really brought things to a halt. But now layers 5 and 4 are inside, behind the interface ring, when they were initially outside the interface ring, outside of the sub, and at the top. Now look how they dipped under and inside. Layer 4, that's the outer part, dipped down 5. So this is 5 inches essentially, dipped down 5 inches and came inside, and brought along layer 4 with it. It's presented to us here. I'm not saying more layers are not also inside, but this is identified by the NIST, and TSB rather. Sorry for saying NIST a couple of times possibly in this video. That it's where we see it now. So 4 and 5 is there. I'm going to end the video with this because, oh my gosh, I got to account for everything, guys, and I will. I will, but it's not, and I have a model already that I've made up. I'm already doing it, but it takes this long just to give you the background data so you can get to where we need to go. And now you can start looking and start using my thought process and go, okay, here's layer 4 and 5. But we know that's past the ring and it's inside. But so it's like that. It's inside. There's layer 4 and 5. That's the bottom. That's where the bottom would have been. So this would have been, this is the tank. It's at the bottom. And we know that tab is, which orientation am I looking at? The hull, outer surface. There's the top. They're saying the top is here. So this is the bottom down here then. So the tanks are up, the tank is now up here. So you now can start figuring out, oh, the bottom was driven up. Did they identify it? Clockwise, D. Hold D. So this is layers 2, 3. Where's number 1? They identified, no. 2, 3, 4, and 5. So one is in there also. Or 1 got flaked off. This might be, it says outer surface. Okay, so we're on the other side at that point. So 1 is in here somewhere. All right, it's in there somewhere. But look at the layers here. 5, 4, 3, 2. And we saw that 5 and 4 are on the other side of this, sticking on the other side of the ring. And they identify on this side, layers 2 and 3 present as coming more internal of it. So it's now looking like the bottom is where the failure was. The bottom experienced the most force going up. Now, can I reverse that? I can if I have the roof, the top part, not the bottom. So if I have the bottom failing, the top failing, well, it fails the top. It starts crushing the top down towards the bottom, and the bottom gets a sort of a cakewalk. It does get the counter force of the outside pressure, the overpressure tries to push it sideways like a sail. So, yeah, I could argue that the roof, the top part, is what failed first. And that's bias now, because I think now that I might introduce some bias, because subconsciously I think I know that 6 is on the roof and 6 is the one that alarmed the most. So it's kind of a bias. But the pieces mostly together, there wouldn't be the ones that wouldn't be breaking up much. And these are all together inside. That's the bottom with the ring. All right, it's with the tank rather. Sorry, hope I don't hang up on you guys. If I do, if I hang up on a video by accident, it's because I pressed the wrong button when I'm talking to you. I pause the screen, edit, things like that between my conversation. So it's an hour and 35-minute video now, but it really took me much longer. So with that said, hey, give me a shout out to the cats. Give me a shout out for the channel, please. Share if you can. Share on whatever, Reddit, whatever you share on platforms. That really helps out. It really does. And then commenting. Sorry, I do read. I read almost all your comments. I just can't respond to them all, and I just don't want to ignore them all with a heart. They put a heart on it. Love, love, love. I did that before, and you know, a lot of your stuff has questions in it. I do read them, and so I think I've read every single 700 comments on the last video. All right, so I do read them, and every now and then I'll respond to, just because I'm like, you know what? I'll answer this one. This one sounds enough that other people might want to know. The other ones, I hope that other people will answer for me, and then they do. And I'm like, good. Yeah, that's perfect. Now, YouTube holds back a lot of comments, so that's great too. I get to read the comment, and then I have to approve it. And often they keep rejecting my approval, but I don't give up. I reset the page. I do it. I approve. Try to approve again. And it's rare that they'll delete it anymore permanently. I go back and check, and I find the message over there. So please give comments. Join in the discussion. But I think this is the roof that failed first, the top, if you will. And that then allows that fractures, so it fractures down. So here's the roof, all right? And let's just do it like a heart shape. All right, so there it is. So we get our failure somewhere around here or here. But I can tell you 100% it wasn't from here to here. This panel's in place. We see this panel in place. All right, there is no bending of it. So it's in place. Now when it bends over, as this piece bends over like that, it can fracture here. Right there, sorry. And then that piece gets blown off. And ultimately it gets blown off in layers. As water pressure comes in there, it can peel off pieces as it was resolving its the overpressure. It can peel off pieces, sections. So the front, you can get your front failing. It starts buckling down the roof deck, if you will. And then the overpressure of the end cap says, "Oh, you're no longer holding me back." It starts driving in, and it peels off the top layer 5. The layer, remember, this is layer 5. It peels off the top layer over here as the head comes in, and we see it scrape that white paint. Remember I talked about the white? It scrapes it off, and it makes it eject off to the left or to the right, whatever position it was in at the time of the impact of the driving force of the end cap. So here's layer 1, but piece of layer 1 that's inner side. Now the other layer 1 is gone. We know that that's their sample they used, but this layer 1 is there, and then the pressure equalizes. Once it equalizes, it's not going to do any more damage. So here's layer 1 and 2, for example. These two, that means water pressure got under layer 1, which is the bottom closest to the inside, and layer 2 and 3, and it pushed all 3 of these off together. All right, so all 3 come together, and that's probably a buckle that threw that piece off from one of the end caps, but it made it back to here. So the whatever end they're saying that is. And then in the background, there's layer 4 and 5. So layer 4 and 5. So layer 1, 2, and 3 are there. And then this is layer 4 and 5 that would have, say, got blown off the top of it through the, when I say blown off, think of it as wind, but it's water pressure. Off it goes, and it sheds down to the ground, layer 1, 2, and 3. And number 4 and 5 is coming down, just shakes off over here. That's considering that this piece fits on top of here. That's considering that. All right, to your left it says hole piece B. All right, we'll just say image of hole A after disentanglement from this is afterwards. So they placed these here. It means jack shit what I just said. They placed them there. Disregard that. Now this is going to say, let me read this down here. You are the forward ends of hole piece A with the individual co-bonded layer labeled. All right, this doesn't say after entanglement, right? So this one did. And let's make sure it's not the same damn piece that we're double dipping on. Trying to look at the profile of it. Yeah, I like this one. All right, so I like this one because, so this is layer 1, 2, 3, and look, layer 4 and 5. How the hell that doesn't make sense? It does. That means that layer 4 and 5, when the water pressure came in, the air pressure, the power washing of it after it was fracturing, it blew off it made it between layers 4 and 3. It grabbed hold of it right here and pushed off 4 and 5 first. Off first. And then as it still came in to finish off, it was still coming in to finish off the last 3 layers, 1, 2, and 3. They go off second. And then that's why they land on top. It looks like it presents as landing on top, doesn't it? Look at the debris. That's interesting down there. You know, what's down there on the bottom. What the fuck? Yo, those little creatures. Little fucking eaters. Little food, little munchers. I wonder what they taste like. That's messed up, isn't it? I wonder what they taste like. Let's zoom in here. All right, so this didn't delaminate. Looks good. You know, it's got some really serious fracture right there on the edge. That's the top layer. And remember, it breaks a brittle fracture, so when it blows off, it brittle fractures the outer ring. Oh, there's some glue. There's some glue still. Layer 1, 2, and 3, they really got splintered up. But I would need to see better look now that you guys understand it. This would indicate that this was huge. That it was flexed all at one time, and I might change the direction of that flex. Yeah, this took the brunt. See how it's booked? It's way open there. I see how small this is, but it appears like it took a brunt of the water pressure. You know, like square force of it. Layer 3, layer 2, and what's this then? Is this part of layer 4 and 5 in the shadows? I get he says layer 3, and I see 2, but this looks integral. Right here. This looks like it might be a full piece. 1 through 5, look. That still looks like he could identify more in this one. So looks like he can identify more of that one. That one's a very interesting piece. But he didn't identify it in here. Oh boy. I'm trying to stop and he just keeps going. Let's make sure what he says first. It's not some unentangled shit. Piece B, layer 3/4 interface showing period, light dark pattern and adhesive. Layers 2, 3, plus L1 underneath, layer 1 underneath, layers 4 and 5. All right, so this would be the peel action I'm talking about. So this is all the layers, 1, 2, 3, 4, 5. And this would be and there's a break right there. You can see it. So water pressure comes in and it peels this back. Whew. It peels it back. It's a much bigger section. It peels back and it breaks it free. The water pressure breaks it free. And now we're looking at what it looks like truly without being harmed by the clamps or any human intervention. There's a serious brushing here. If we can book it over here, then we know where it came from. And I think we can book it. That we close it over like a book, and there it matches up. So yeah, that's a water thrust. Whew. Getting in there. Man, we only knew exactly where that piece was. That would be so telling of the water pressure on that one. And once you put them all together, you have the story. This says, image of piece B showing crack on the surface. Showing cracking on the surface. So this would be layer what? Image B showing cracking. They don't identify the layer, but I'm going to guess it's layer 5, the outer layer. That's the outer layer, not another layer. They got driven in. Remember how I said it sheared off, so it sheared this off. So inside here, still in all the debris, we should probably still find the interface ring. The interface ring has been crushed or mangled. I don't think it escaped. I think it's still in here. So they should be able to show that to us. And it would probably look like the model kind of kinked in like this, like a pretzel. All right, here's layers 2, 3, and 1. So 1, 2, 3. This is, and in the background there's more, but, oh, this is the peeling? No, it's not the peeling piece. This is where you would pick, remember I said I was biased on this? But it says, after removal of layer 4 and 5, the fracture along the counterclockwise edge was irregular. So they removed to bring it up, so it was all one piece. But this would be sort of a buckled piece in this circle. And buckle piece, I'm just going to do that like, something like that. And then you get the water pressure coming in, peeling off layer, peeling it off, ejecting layer. The end caps, all of a sudden the end cap pressure is still there. It closes in and starts pushing off layers also and sending them off, ejecting them. Piece B after removal. It's again after removal, so it's a lot of corruption in that data, so I can't really use too much. Image of piece D showing the sigmoidal buckle as a yellow dash. So this would be sort of like what it would look like the buckle down. It would be there, sort of like the one I just showed you. It would be, yeah, I know it doesn't look like a box. So this piece like this would be the piece we're looking at here. And so it wouldn't actually be a buckle from, the water pressure like that. It could be a starting point is what I'm driving at. It would be the starting point. More like here. And what layer is it? So this is layer 4 and 5, 2 and 3, and inward bend. Yeah, okay. So yeah, he's getting the drift. This guy's, he's not somebody who plays video games on the side. He pays attention. Of course you miss a couple of little things, but so do I now and then. Then you come back and look at it again. There is maybe the flip side version of it, piece D from another point of view. All right, so this is piece D? Yeah. All right, so let's look at the other point of view. Yeah. Okay. But the claw is there. The claw is there, but this would be it here then. These are the pieces that meet. This would be my piece that I would see as a failure point. It's biased, and I think he's going to come to the same conclusion, and it is biased on both our parts, but this would be the literal location, but here's a circle, and that same circle, I'm going to do this. that this is the part that buckled down. It failed. It has to fail through all the layers. And sure enough, this looks like, damn, it looks like all the layers. And from that point, you get the end caps wanting to come in and say hello to the back cap, and pressing the, it ejects this too from the roof. It starts coming in, the end cap's pressure then takes over and jams in and then pushes this back out. I don't know where this location, I wish I had more images. Let me screenshot this. And I hope this is the last image. Yeah, these say, interesting, it says, based on residual marks left by the drop weight assembly attached brackets. The short sides of the rails in view are most likely the lower sides based on residual marks left by the drop weights. Remember I said the drop weights might hit this thing? Well, apparently the drop weights can hit it. And interesting. Oh, there's booking in the back. So there's the layers there. There's that one. I think we already showed that one. I think he showed it in another one, but there's multiple covered layers. Ending the video. Please comment, give the shout out to love. We already gone over this shit. Shout out and love to the cats. Shout out to you guys for tolerating this long ass video. And I will put together a model, but this is where we're going. Like something like this is where we're going into. Something like this is where we're going to use our starting point. Yeah, let me just look at it a little bit longer. All right. Yeah, I'm really crushing on this as a starting point. Right there. Yeah, because we have this bend here. The other one would be behind here. This should be our location of that part. And then we have it, this should be compressing in also on the rings. On the rings that start the shearing action. And if this lines up with those rings where he gets stuck for that striation part, it will be, verification. All right, love you guys. Give a shout out to the cats. Keep talking. Keep writing your comments. I am reading them. Sorry I'm not responding to them. If you really don't need me to respond to them, say, please respond. And I guess I can try, but YouTube does not pay me. I know they monetize my shit, but I don't get paid. All right, they told me I made $40,000 or something like that, and I'm like, you know what? Report me to the IRS then for saying I made $40,000 over my channel's lifetime, because you never sent me that $40,000 check. I saw it in the algorithm in the thing there. I'm like, you gotta be. Of course, other channels make way more than that, but I didn't make $40,000. I'm like, yeah, report that to the IRS then, because you're gonna owe me the interest and everything else on that money. Let's do it. And you know what? I just made a mistake. I'm not supposed to be fighting with YouTube because they can shadow ban me for that. So you know what? Please disregard the last statement. YouTube is letting these videos go out right now without banning them. So I appreciate you, YouTube, for that. And I was wrong for being a dick just then and coming after you. I apologize for the person that watches my channel. Please accept my apology. Thanks, guys. Love you. Bye.